I have the honor in a virtual symposium to be the virtual version of Jan Pokorný and speak to the slides that he presented. And I apologize up front that I will miss you will miss the nice accent with which Jan speaks his English and get a Dutch version that you've already heard before. But we really have cool insights that come from this work on the Earth's surface temperature and the very compelling way of imagery, of showing that to people what it looks like, which really shows that vegetation cools. And the fundamental role played by water and vegetation in the climate is indeed that direct cooling effect that we have only partially represented in the current models and our current understanding, partly because the weather stations excluded that effect for a long time. So the basic content is if we start the energy, the solar energy is driving the whole hydrological cycle, and there is variation in that we need to know. It's the balance between evaporation, water going from liquid to vapor, and vice versa, that has big effects on the temperature. And we can really see this as the air conditioning part, and it will end up with showing these thermal pictures. So if we do the basic balance of the solar energy arriving at the surface or the top of the atmosphere, then there is variation between seasons, as we see here in the difference between January and July, and there's difference between years, and there is parts on that. There is variation between many factors in the detail of solar energy at the same time that is driving the hydrological cycle. The accuracy with which we can measure solar irradiance is about 1% at the moment. Well, you've seen pictures like this before explaining the greenhouse gas effect, how greenhouse gases in the atmosphere interact with that. But of course, clouds and water vapor has an even stronger effect on that than gases like CO2 and N2O. And we can relate the radiative forcing to the temperature of any specific place by looking at what is reflected and what comes into it. And of course, we all know that if we compare a cloudy day on the bottom in the graph with a sunny day, that we have very different levels of irradiance reaching the soil surface. Well, the cooling effect of these clouds, we can get a sense of that if we look at nuclear power stations, as we still have in the Czech Republic, and you see that they actually need a lot of water cooling to keep the nuclear power things going. And we get a sense of the amount of water that they need to evaporate to cool the system and to keep it, and compare that with the cooling that happens on a unit of land area. And what we get if we combine the solar energy flux with the water balance, we can see the two things that there is a lot of. If we would compare on the left-hand side a drained field where the evapotranspiration is relatively low, we see that it produces a lot of heat, whereas the patch on the right-hand side with trees and ponds of water, they evaporate a lot of water, and that is called latent heat, but it actually means cooling effects. So there's a direct link between the evapotranspiration and the heat flux, and we get a sense of the amount of energy involved with energy consumption when we vaporize, when we go from liquid to vapor, and at the same time energy release in the reverse process. So condensation takes energy, whereas vaporizing takes energy where condensation produces, and I think that's partly linked to what Douglas was talking in the previous talk about. Well, these things are not particularly new. They have been understood for quite a while, and when we go back to the thermodynamic analysis of the past, we can see that temperature and water are directly linked, but it has not yet been fully applied to land cover types and land cover surfaces. And the group of Jan has been working on thermal imagery by various ways, in this case balloons that took, with thermal cameras, recorded the surface temperature of landscapes somewhere in the Czech Republic, as we see here, and studied that during the day. And what we see here is graphs of the daily warming and cooling that we see over patches in that same landscape, and it's all exposed to the same solar radiation. It's in the same location. But we see obviously that the asphalt, the tarmac road, is by far the hottest in the middle of the day, and the forest is slightly warmer than the open water, but not that different from it. An older stand is in the same. A wet meadow is still evaporating quite a lot, transpiring a lot of water, but a harvested meadow, which is a dry patch, is actually getting very hot during that part of the day. And one of these figures is included in the paper by David Allison that we are discussing here. So the remarkable thing is that at short distance from each other, we have very different surface temperatures. At the same time, if you walk in the landscape yourself, these things are not a surprise. You can easily see it and feel it. But if we look at the daily range of temperature and the surface temperature, we see easily differences between vegetation and land cover types of 15 degrees, in some cases even more than that. Yeah, and we get to the temperature that people feel and experience is not the same as the temperature that the weather station has been recorded. It's not the temperature that you see on the climate maps. There's a wide range of actual temperatures that occur. And changes in land cover are directly linked to that surface temperature and are a way to manage the temperature under which people live. Now, a further application that Jan has been involved with is a study of what it means in the Mau forest in Kenya. And of course, all our colleagues in Nairobi will be very much aware of how hot the discussion about the Mau forest has been. This is a contribution on the biophysical side of that story, and which has been published in 2010. Yeah, so the Mau forest is one of the few remaining closed canopy forests within Kenya, and it feeds 12 rivers that feed into 6 lakes, and it is an important part of the hydrology of Kenya. At the same time, the discussion about it was heating up a lot when a new hydropower plant was constructed that needed the water generated from the Mau forest, and it brought back this awareness that actually there is a lot of encroachment, a lot of conversion of the Mau forest going, and the government decided to evict people from that, which has led to many discussions and conflicts on the social side. On the hydrological side, we can see that this is a color image interpretation of the thermal part, that we see that the forests stand out as having a very different temperature than the farmland that is adjacent to it. And on the ground, if you go there, you see many evidence that people are cutting trees, are using it as firewood, are taking it out on smaller scales. At the same time, a lot of the forest is converted to farmland and to half-open vegetation, which has consequences on the ground for local livelihoods, but it also has influences on the water and the hydropower supply coming from that landscape. But we can also, and that is the work that we contributed here, it has direct effects for the surface temperature and the cooling part on this. And this is an analysis of the land surface temperatures influence of the forest conversion that has taken place. And yeah, there is in the paper the detail of what it looks like on the ground, but a strong shift from closed canopy forest to open vegetation. And we see that back in the temperature pictures of that area, and in that way it has impact on the surrounding landscape as well. So this is somehow related to the previous speaker, to Doug, who talked about the water pump theory. Actually, people within the Mau forest area themselves they have read the papers of Douglas Hill and Modiarso, but they are convinced that forest does indeed attract rainfall, and they have decided to keep a 600-hectare patch of a forest intact for it. And yeah, what the group here has been doing is taking thermal pictures of that area and seeing whether that matches the local perceptions of what it will do. And these are pictures taken from an infrared camera on an airplane. And indeed, we see strong effects on the temperature. This is an example of the deforested part, where you see a lot of reds and yellows coming in, and the darker colors here are the closed canopy forest, which still has intact evapotranspiration. If you compare that with an agriculture field, you see even within an agriculture field there are hotter and even hotter places. There's variation on that front, but it is in a very different category from vegetation that has a high rate of evapotranspiration. So I think the main message coming out with that work is that it is possible to visualize the surface temperature, that these infrared pictures combined with normal pictures do help make the story very clear to people that forests are cool, that evapotranspiration is a cooling effect, and that we can in that way directly relate the hydrological cycle to temperature. And this does seem to be aligned with the Makareva-Gorshkov biotic pump theory that Douglas was explaining to us before. We can also take this into the further analysis, and that links back to Cindy's presentation yesterday of thunderstorms, cyclones, and wind and heavy rains on that front, and see that temperature itself is the cause of turbulence in the atmosphere, and links back to the pattern of rainfall that we see. Now, on the physics side, we can quantify the fluxes of energy linked to the fluxes of water in this part, and it supports the basic concept of bringing back vegetation, bringing back water use as a way of cooling the planet. If you take the same methodology to the urban areas, you see huge differences in temperature in the same place. These are more or less the same time pictures. On the thermal picture, you see a person, on the normal picture not. But there are these effects going on. So I think the bottom line of the presentation is that that cooling effect is very well understood in physics. It is very well understood in anyone who plants trees around their own place to keep it cool. It is not completely represented in the current climate data because they have been collected on places without trees, and it is not fully incorporated in the current generation of climate change models. But there is a clear link between what people on the ground think and believe and why they want to keep forests and our current understanding of these processes. And again, I apologize for the many points I missed if Jan would have given this talk himself. Thank you.
Yeah. Thank you, Pak Maine. Shall we give applause, Pak Maine, in real terms?